Well, we made it to the end of the chapter. So like I promised before, we're going to be bringing together previous chapters with the content of the chapter in gases to be able to do a stoichiometry, basically mole-to-mole relationships based on balanced chemical equations. So stoichiometry. And let's begin with a problem like this. Methanol, CH3OH, that's what that says in there. So methanol can be created by reacting carbon monoxide and hydrogen gas. And the relationship is going to be 1 carbon monoxide for every 2 hydrogens to produce 1 methanol. So those are the moles to mole ratio that we are going to have. And the question is how many liters? So we're trying to find the amount of liters of hydrogen gas. So how many liters of hydrogen gas with a pressure of 748 millimeters of mercury at 86 degrees Celsius, which we know we have to change to Kelvin, which is going to give us 359 Kelvin, are required to synthesize 0.55 moles of methanol. So given 0.55 moles of methanol, can we go all the way to liters of hydrogen gas required? This is an stoichiometry problem, so we're going to use the train track method because we care less about the moles of methanol. We're trying to find the moles of hydrogen gas, right? And according to this balance equation, for every 1 mole of methanol, you have to have 2 moles of hydrogen gas. So the moles of ethanol will cancel. And when we get the moles of hydrogen, can we get the liters of hydrogens? Yes, we can do that if this is STP conditions. You can continue and use the train track method all the way to liters if this was STP conditions, because you know that 1 mole of hydrogen is going to equal 22.4 liters of hydrogen. So 1 mole of any gas at STP is going to be 22.4. However, these are not STP conditions. STP conditions are 0 degrees Celsius, 1 atmosphere. So this is not STP condition. So you cannot use this. You cannot use that. That's only for STP. So in other words, your train track method stops there, and it's going to give you the moles of hydrogen. So let's see how much is that. So we're going to have to be happy with only being able to find the moles of hydrogen. So 0.55 multiplied by 2 equals 1.1 moles of hydrogen. So that's what we have. We found that we have 1.1 moles of hydrogen required to react with 0.55 moles of methanol. Pure and simple stoichiometry. We haven't used anything with gases yet. However, that's not what the question is asking. The question is asking us to find the liters. So how do we do that if we cannot use 22.4 liters equals 1 mole because this is not STP? Well, there's only one way to do that. We're going to have to use the ideal gas law. So with the ideal gas law, we know that PV equals nRT. We're looking for the volume, liters, right? So we're gonna divide by P on both sides so that we can cancel the pressure on the left side and leave the volume all by itself. So we're gonna plug our numbers. So we know that we have 1.1 moles of hydrogen because we found it at the beginning of the problem. We know that our R is 0.08206 liters times atmospheres over moles Kelvin. And we know that our temperature is 359 K. And our pressure, it had to be in atmospheres, but what we have is 748 millimeters of mercury. So right on the formula, you can convert this to atmosphere because 1 atmosphere equals 760 millimeters of mercury. And we put all that together and let's see what do we get. So that would be 1.1 multiplied by 0.08206 multiplied by 359 divided by 748 divided by 760. And that's going to give us 32.9 liters. So to be able to burn or react 0.55 moles of, to be able to produce 0.55 moles of methanol on this reaction, we're going to have to use 32 liters of hydrogen gas, which is going to be at 359 Kelvin with a total pressure of 748 millimeters of mercury. So you saw how we just did standard stoichiometry problems, and then the result, we have to use the ideal gas law to find what we were looking for. Like I mentioned before, it would have been a lot easier if we had been dealing with STP. So let's see what else we have. So now we're dealing with STP, measure at STP. So the moment you say measure at STP, you have two choices. You can say temperature is 273 Kelvin and the pressure is 1 atmosphere, but you also know that at STP conditions, 1 mole of any gas equals 22.4 liters. So that would be 1 mole of any gas at that temperature and pressure. So the question is asking how many grams of ammonia, so that's what we're looking for, grams of ammonia, that's our target. How many grams of ammonia form when you have 28 liters of hydrogen gas? And here's our balance equation with our mole to mole ratio. So from hydrogen gas, we need to find ammonia. But we're not there yet because we cannot do a stoichiometry with liters. A stoichiometry can only be done with moles. So you're going to have to convert the liters to moles first, which is no problem because at STP conditions, 1 mole of hydrogen gas is going to have to be 22.4 liters. Any gas at STP condition will follow that. So that allows us to cancel the liters and leave us with the moles. So now that we have moles, now we can use the stoichiometry the way we know it. So we don't want moles of hydrogens, we want moles of ammonia. So we're going to get rid of the moles of hydrogen. So that's going to cancel. And according to the balance equation, you got 2 moles of ammonia for every 3 moles of hydrogen. So the only thing we have right now is the moles of ammonia, but we don't want the moles of ammonia. We want grams of ammonia. Well, no problem. We know that 1 mole of ammonia, so that allows us to cancel the moles of ammonia, equals 17.0 grams of ammonia. 1 nitrogen, 3 hydrogens, that's 17.0. So when we do that, so there was no need to use the PV equals nRT or the dear gas law, because we're using the molar volume. Molar volume is the volume of one gas at STP condition. So what do we get on these problems? 28.8 times 1 times 2 times 17 divided by 22.4 divided by 3 divided by 1. And we get 12.5 grams of ammonia. So if you want to be able to consume a total of 28 liters of hydrogen gas at a standard temperature and pressure or STP conditions, you're going to need a total of 12.5 grams of ammonia. And that's how we solve that problem. So once more, since we're dealing with STP conditions, there's really not a need to use the ideal gas law. So with that, you should be able to do that problem. And when you're done with that, you should be able to do this problem. This one is going to be STP conditions. And once you do that, we will say that pending more practice on your part on Alex, you know now how to do stoichiometry problems involving gases. Because the PV equals nRT allows you to find the moles, and then you can do stoichiometry with the moles. We're going to see on chapter 12 that you can do the same with solutions by using molarity. So that's in the future. That's coming soon. And that brings us to the end of this chapter. So what do we understand better now? We understand better the kinetic molecular theory. And we see how that relates to the properties of gases, pressure, volume, temperature, and amount. Hopefully we understand better what pressure is, which is a force exerted over a specific area. We saw how we use different conversion tables to go from one type of pressure unit to another one. And that's the case because different countries use different pressure units. And pressure is a thing that we have learned through the years. So we have changed it based on the technology needs. And with that, we saw how there's several different laws, like the Boyle's law, P1V1 equals P2V2, where the pressure is inversely proportional to the volume. We saw the Charles law, T1 over V1 equals T2 over V2. We saw the combined gas law, which combined those two, Boyle's law and Charles law. We also saw Avogadro's law, where the number of moles is directly proportional to the volume of the gas. We have done a lot with the ideal gas law. And we saw the Dalton's law of partial pressure, where it said partial pressure of one gas in a mixture plus the partial pressure of the second gas plus the partial pressure of the third gas is going to give us the total pressure. And then we just did a stoichiometry involving gases. And that covers the whole chapter, which brings us to the end. So this is a milestone. We're finishing chapter 11, one more chapter, and we will be ready for test number 4. And from there, really fast, we will move into the final and we will close the course. So take care. It's been a pleasure spending this Saturday with you. It took me the whole day to do all these recordings, but I want to get ahead so you have more time to listen to this. So until the next one, see you soon. Have a wonderful weekend.